This course covers statistical process control from entirely practical approaches. It takes you from the concept of a process and a system to control charts to process capability analysis and finally to the Six Sigma applications in business and manufacturing. The speaker and author of this course is one of the top statisticians and quality control experts, particularly in the fields of textiles, cotton processing, non-woven, spinning, weaving, knitting, and apparel industries. Dr. Yehia Elmogahzy was a professor of statistics, statistical process control, and quality control for 25 years at Auburn University, Alabama, USA before he led his own consultant company in 2013. This is only a very brief review of the course, which expands over 50 hours.
We'll talk about control charts as the first part of SPC, and we will go over the different types of control charts, the different categories of control charts. We will present case studies, many examples, and after that we will move into the issue of process capability analysis, which is part 2 of this phase. Statistical process control. What is a statistical process control? As I mentioned earlier, process implies material, machine, methodology, people, many elements. The 5 basic elements that typically describe material are the ones that are listed here. Material, machine, method, people, environment. I may add energy. And a process can be as simple as one of these or 2 or more of these. Okay? If you are in the manufacturing environment, everything that has to do with this environment is a process. In this regard, I like to clarify the difference between the term system and the process. As I just said, a process can be one or more of these 5 basic elements. A system, on the other hand, is an entity that has inputs and outputs. So a machine, which is one of the process elements, may also be considered a system, which has inputs, outputs, and noise, because there is no such a perfect system that operates without noise. In many situations, we're going to see what we call automated SPC program, where not only that we monitor and detect variability, but we also have online capability that takes the signals of high variability or out of control variability and correct it online. That's a system that we built in or we design to take or to make use of the SPC results and correct. So although control is an essential issue of SPC, after all, this is the goal. The goal is not just to look at ourselves in the mirror every morning. The goal is why we're looking at the mirror. Why SPC? It is to develop products, okay? It is to plan manufacturing, is to mass manufacturing wisely, is to monitor the process, and to solve problems. And all of these activities, okay, make use of the SPC outcomes. As one review these different phases of the make of a product and ask about the common challenges facing engineers, manufacturers, business people, marketing people, one will find that the three most commonly faced challenges are insufficient information, subjectivity, and variability. Let's talk a little bit about each one of these. So the primary phases of SPC, again, quality priority layout, in which you lay out all your quality problems and you start with the most important one, often the one that costs your organization the most. Secondly, you have to have testing and monitoring facilities. Third, you have to have ways to analyze the data obtained from testing and monitoring. Fourth, you have to have committed attitude toward correction and prevention actions. And finally, you have to be able to document on continuous basis the improvement or the deficiencies of your process. Quality priority layout. Companies can divide their quality parameters into critical and routine. When we say critical parameters, this is something that have to be decided in the context or in view of the organization. Okay? If you go to a textile mill that produces fabric, perhaps the most critical parameter is loom stops, or loom efficiency, or fabric defects. Okay? These are critical because they are directly influencing the cost. More importantly, they are directly influencing the consumer or the customer perception of the product or service, especially in the context of a competitive strategy. And routine quality parameters, as I just said. In an automobile airbags, here are some of what we call it critical parameters. The inflatable material performance. In case of an accident, if the inflatable material, if the bag does not perform, the customer will know that. And that's a whole liability issue. The deployment mechanism. Not only the speed at which the airbag is going to be deployed, but more importantly, the impact of the airbag on the passenger, which is a new issue. And then the sensor mechanism. These are critical parameters. Yet these parameters are fully supported by what we call routine parameters, such as material thermal properties, material type, velocity change of the vehicle, material physical properties, fabric design. So one can see from this example that, again, critical parameters are the parameters that are directly felt and realized by the consumer, while routine parameters are extremely important, but they are not directly realized by the consumer, but they definitely affect those critical parameters that are fully sensed and realized and judged by the consumer. A control chart concept simply means collection of data on daily basis and determining what we call the data statistics, or the average of every day, or the range or the standard deviation, and then plot these data or these statistics, whether it is the average or the standard deviation, on daily basis, okay, and establishing control limits, upper control limit, lower control limit, a center line, and The goal of using a control chart is to see whether the points representing the process parameter are within the control limits, the state that we called early a state of in control, or outside the control limits, which is the state of out of control and the state that indeed requires an action. A control chart is a simple two-dimensional graph that is used to systematically monitor the variability in the values of any quality parameter produced by perhaps one or more of the basic process elements. It's a two-dimensional graph. The horizontal axis here represents time. It could also be location. It could be machine number. And the idea here is a control chart can be used to monitor any event or changes in process, whether on time domain or time increment or location increment or machine type, lot type, factory type, and so on. The vertical axis, on the other hand, represents the variable in question. The strength of material, the weight, perhaps rejects or number of defects. That is the vertical axis. As we will show shortly, we calculate points to be plotted on the chart, and these points reflect the changes of the quality parameter values on daily basis. They can be individual values, they can be some statistics such as the average value, the standard deviation, the range. And as we mentioned earlier on, the idea here is plotting the points allow us to see the points being either in control, that is within the limits or within the control limits, or out of control, that is outside the control limits. And as we mentioned early on, points within the control limits are considered to be natural point or common cause variation points due to only randomness or due to the fact that variability is an inevitable outcome. While points outside the control limits are due to assignable cause variations. These are the points, the red marks are the points that we need to be concerned about. The power of a control chart stems from the fact that it provides a simple way to display the pattern and the source of process variability. In statistical terms, a process population should be described using what we call measures of central tendency. These are measures around the center, and measures of variability or dispersions. These are measures indicating the deviation of these points here or these bars here from the center. So it is very important to understand this fact. And these are statistical facts, that any process should be described by measures of central tendency and the measures of variability. Well, the control chart does exactly that. The bottom slide here, you should be familiar with it by now because we displayed it before. We told you that we begin with this simple histogram, simple fact, where we collect the data every day. Okay? And then every day we collect the data, and every day we look at some measures of central tendency or some measures of variability, and we plot these in a two-dimensional graph. So you can see here that the points on the control chart may be a result of descriptive statistics that we repeatedly do every day, from which we get points summarizing the performance of the process on daily basis, plot these points in the control chart, and then examine whether these points are within the control limits, or in a state of in control, or outside the control limits, or in a state of out of control. Let's talk a little bit about sigma, since it represents the key parameter of a control chart. Sigma should always reflect the variability or the standard deviation of the points being plotted on the chart. Now, these points may indeed be individual points. If we're testing cars, then every point may represent a car, because we simply cannot take 20 or 30 cars every day and test them. So in this case, really, we are talking about every point on the chart representing an individual observation. And later on, we're going to discuss individual observations control charts. If indeed all what we can do is one component or one individual observations, then sigma that we use to establish the control limits will have to come from somewhere, which in this case will be the population standard deviation. One would say, how are we going to know the population standard deviation? Well, we can test a massive amount of cars, or we can rely on historical data to bring about the standard deviation of the population. So for individual points charts, it is the standard deviation of the individuals that we consider in establishing the control limit. That's the 3 or plus or minus 3 sigma. Very good. If on the other hand we have a subgroup plotted on the chart, meaning a group of numbers, and the point on the chart is a summary, say the standard deviation or the mean value of a subgroup. So now we're no longer dealing with an individual component, we're dealing with a collection of components. This is a whole sample that may have a size of 20 or 25, as you can see here, every day. And what we're plotting on the chart here is perhaps the average, x1 bar, x2 bar, x3 bar. What would be the standard deviation in this case? The standard deviation in this case should be the standard deviation of averages. In statistics, we call this the standard error. A control chart is a process of a continuous test of hypothesis of the points plotted on the chart. We also mention in statistics course that when you perform a test of hypothesis, you ought to be very careful, because you may be committing one of two common errors: the type 1 error or the type 2 error. The subject we are about to discuss is the so-called 6 sigma. 6 sigma is one of the more recent approaches of quality improvement. And as always the case, any new quality program introduced to the market is associated with some catching phrases and some attracting or appealing points, as if it is very difficult often to get the people attention. Every approach should be acceptable and should be considered, yet the ultimate approach should be customized by the organization in view of its product or service type, structure, qualification of people, competitive status. One of the main reasons is that different approaches, each one has its own merits. It's just hard to reject or even argue too much with an approach, especially in the general or universal sense. The story of Six Sigma is somewhat unique. In 1981, Bob Galvin, who was the chairman of Motorola, challenged his people, challenged his company to achieve a 10-fold improvement in performance over a 5-year period. So here is an executive that believed so much in quality, came to challenge his people to achieve a 10-fold improvement in quality in 5 years period. Our defects have to be reduced by 10-fold. Our customer dissatisfaction has to be reduced by 10-fold. It's a generalized challenge, but each sector and each segment in the organization can seek ways to first quantify, the type of defects, and second, reduce it by 10-fold as the chairman requested. As we speak of Six Sigma from an analytical viewpoint, we're going to find that Six Sigma can be narrowed down to one single aspect that we discussed in previous session, which is process capability. Six Sigma, however, entered the issue of process capability analysis or the issue of process capability from a completely different view than all the classic views of capability that have been entertained in the past. But analytically, it's the same analysis. In the past, process capability was viewed as meeting customer specs, meaning our control or inherent or natural limits fall within the customer spec limits. And the focus on process capability analysis was, if you recall, was always upper spec, lower spec, or sigma of the process. So it was the variability or really the stretch or the compression or expansion of the normal curve. The Six Sigma entered that area, that field of process capability from a completely different angle. And the angle was simply that, what if the whole process was recentered? So now we have the normal distribution. We are not going to be talking about compression, low variability, or stretch, high variability. No, we're going to talk about moving the entire process from one center to the other, which can happen. That is how the Six Sigma approach began. And in that sense, the key question was, can a process actually encounters a recentering that's going from here to here and still be capable, still meets the customer specs? That is the analytical foundation of Six Sigma, and we will explain that by examples very shortly.